Okay, in section 6.6, we're going to look at the normal distribution, and we're going to use it to approximate the binomial probability distribution. So in this problem it says, what's the probability of more than 4 passengers who do not show up for a flight? So we'll have the binomial probability distribution. And we write this as the probability of x, and it equals our combination formula we saw maybe back in chapter 4 a while ago. And that's n factorial over n minus x factorial times x factorial, where you have n trials and you want x successes. That's times the probability p, which is the probability of success, raised to the x, which is the number of successes, times q, which is the probability of failure, raised to the n minus x. So that's the formula, and we did several problems with it in the past. Now there's a problem here because if n is too large, say 1,000 or so, then this whole formula will break down. In fact, you can try putting n factorial in your calculator, and it's likely that unless you have a very expensive calculator, it'll give an error. So what are we going to do? Well, the whole point of today is we want to use the normal curve to calculate areas that are then probabilities that would replace this formula, which can be clunky and break down on us. So here we have the normal curve, and we can find some area, which we've had lots of practice doing. And then that area could be the same as the probability calculated using the binomial probability formula. So all we need to calculate an area of a normal curve is mu, the mean. And for binomial mean, it's just the number of trials n times the probability of success p. And then we need standard deviation sigma. And for binomial, that's just the square root of the number of trials n times the probability of success p times the probability of failure q. And we'll see lots of examples of calculating this formula throughout this section. Okay, so in this problem, we want to use a continuity correction to describe the region of the normal distribution that corresponds to the indicated probability. Probability of more than 4 passengers who do not show up for a flight. First, let's talk about this continuity correction. So in this problem, it's the probability of x being more than 4 passengers, but let's start with an example where we say, what if it said probability that x equals 4 passengers? So what's the probability that exactly 4 passengers do not show up for a flight? Under the normal curve, x equaling 4 is a line. And then we're asking, well, the probability of this would be the area of this line. So what we're going to do is we are going to change this problem into, we're going to add some area to this, and I'm going to exaggerate this. So this would not be this wide, but just for the sake of argument so you can see it. So this continuity correction is going to say, well, let's subtract 0.5 from our number and let's add 0.5 to our number. And now we can get a rectangle. We can get a width to this thing. And therefore we can actually calculate an area. So in all the numbers they give us today, we're either going to subtract 0.5 from the number or add 0.5 to the number. So you're never going to use the numbers they give you today. You're always going to continuity correct them with either minus 0.5 or plus 0.5. So now we look at the idea of more than 4. And there's two possible drawings we can make. So we can write 3.5. That would be if we subtract that 0.5. Or we can write 4.5, in which case we added that 0.5. Now, more than 4 indicates that they do not include 4. So if we look at our two drawings, in the first one, if we identified where 4 is, it's to the right of 3.5, and it would be to the left of 4.5. So which drawing does not include 4? It would have to be the bottom one. So we're going to use a continuity corrected number of 4.5, and we want the area to the right of it. Okay, problem 52. We're going to check the condition that, this is from the binomial distribution, there are 4 conditions, this was one of them. If m times p is greater than 5 and n times q is greater than 5. So that was a condition where the sample size n has to be large enough and your probabilities p and q have to be large enough so that if you multiply those two numbers together, you'll get values greater than 5. Helps us pick a big enough sample size. So estimate p more than 4 with n equals 11 and probability of success is 0.4 by using the normal distribution as an approximation to the binomial distribution. If n times p is less than 5 or n times q is less than 5, then state that the normal approximation is not suitable. So this problem is pretty simple. We just have to take n times p and n times q. Now, if they give us p, we can immediately write q. So those two numbers have to add up to 1. So if p is 0.4, then q is 0.6. N was stated as 11. So we'll take 11 times 0.4, and we'll take 11 times 0.6. For the first one, that's 4.4. And for the second one, that's 6.6. Now, we want both those numbers to be bigger than 5. If either one is not, then we have a problem. So we see that 4.4 is less than 5. So that's going to tell us the normal is not suitable. So the second one, even though it is bigger than 5, we're not going to be able to use it because one of them was less than 5. So the normal distribution cannot be used in this problem. It's kind of basically saying the problem size is too small. Okay, in problem 53, Use a normal approximation to find the probability of the indicated number of voters. In this case, assume that 116, that's n, eligible voters age 18 to 24 are randomly selected. Suppose a previous study showed that among eligible voters aged 18 to 24, 22% of them voted. So that's 22% is going to be our p-value, 0.22. So we can immediately write our q value, which would be 0.78. Those two add up to 1 again. What's the probability of fewer than 30 voting? So we're not including 30 because of the words fewer than. So we draw our normal curve, and we're going to identify where 30 would be. And since we want fewer than that, we're going to shade those areas to the left. So notice we have two conditions, 30.5 and 29.5, a case where we subtract a half and add a half. Where is 30 on each? You can see it's to the left of the top one and to the right of the second one. We don't want to include 30, so the first one's out. So we're going to want to use the number 29.5. So we want x to be less than or equal to 29.5. To use this, we have to convert it to a z-score. A z-score is x minus mu, but we haven't found mu yet. Divided by sigma. So to find mu and sigma, those two unknowns for the z-score, we'll use the formulas that we gave at the start of class. So mu is just equal to n times p, sample size times probability of success. In this problem, n is 116 and p was 0.22. If we multiply those two, we will get 25.52. Sigma is equal to the square root of n times p times q. And we just found NP, that was 25.52, so we can put that right in there. Just multiply by q, which is 0.78. Take a square root. And we find our sigma to be 4.46. Now we can use that in our z-score calculation, so we'll take 29.5 minus 25.52 divided by 4.46, and we will get a z-score of 0.89. So what we're really trying to find is not 29.5, we're trying to find the area to the left of 0.89 z-score. So we go to our z-score table. We've seen this many times. We look for 0.8, and then the second digit's a 9, so the top row, we go to the 9. See where those two intersect, 0.8 and 0.09, and it would be 0.8133. So that area is 0.8133. or 81.33% chance that fewer than 30 people will vote in that age demographic. Okay, problem 54. Got a gender selection technique designed to increase the likelihood that a baby girl will be born. In the results of the gender selection technique, 979 births consisted of 507 baby girls and 472 baby boys. In analyzing these results, assume that boys and girls are equally likely. Find the probability of getting exactly 507 girls and 979 births. So when they say equally likely, what they mean is that P is equal to half and Q is equal to a half. So it's like a coin flip, 50-50 chance. So to find the expected number of girls, or the mean number of girls, we would take N, which is 979, times P, which is 0.5, and we would expect 489.5 girls. The standard deviation is equal to square root of NP times Q. We just found NP, so we can plug that number in there. 489.5 times Q, which is another 0.5. Take a square root, and we'll get 15.64 standard deviation on the births of girls. Now, looking for exactly 507 girls and 979 births, we're going to have to change that 507 because that's the area of the line that we talked about in the first problem. So instead, we're going to sandwich that x value between two. We're going to have 506.5 on the low side, and we're going to have 507.5 on the high side. So again, subtracting that 0.5 and adding that 0.5. But we need to convert those numbers to z-scores. So it'll be instead 506.5 minus the mu, which is 489.5, divided by the sigma, which is 15.64. That's now going to sandwich z, because it's now a z-score, which is sandwiched on the right by 507.5 minus the mu, 489.5, divided by the same sigma, 15.64. That's the probability that our z-score is sandwiched between 1.09 and 1.15. So if we draw this on the normal curve just to get a look at it, and I'll exaggerate this again, it wouldn't be quite this wide. It'd be 1.15 over here on the right and 1.09 on the left. And we're looking for that area. And we've seen this in the past. So the way we do it is we take the area of the bigger z-score, the 1.15. Then we find the area for the smaller z-score, the 1.09, and we subtract those two numbers. And the z-score for the area for the z-score of 1.15 is 0.8749. I'm not showing the table again because we've done it so many times. The area for the z-score of 1.09 is 0.8621. And we just have to subtract those two numbers to get the area in between them. And if you do that, you get 0.0128. So there's a 1.28%, not even a 2% chance that there'll be exactly 507 girls born in 979 births. Okay, now we're going to look at the probability of 507 or more girls in 979 births. So or more includes 507. So we're going to have 506.5 or 407.5. But since we're going to the right, the area is going to be to the right, we have to go with the smaller number so that we include 507, which will be to the right of it. So we want the probability that x is bigger than or equal to 506.5. Or we want the probability that the z-score is greater than 506.5 minus that 489.5 divided by that 15.64. But we can use the fact that we already calculated the z-score to be 1.09 above. And in fact, we already know the area for this is 0.8621. So we draw our normal curve. We know the area to the left of 1.09 is 0.8621. We found it earlier. So to find the area to the right of it, we just take 1 minus that 0.8621. And we'll get 0.1379. So that would be the probability of more than 507 girls. So now we want to know if boys and girls are equally likely. Is 507 girls and 979 births unusually high? Well, we were expecting 489.5 girls out of this many births. 507 is only 17 girls above that approximately. So it's not really an unusually high number. It's actually pretty close to the mean number of girls that we'd expect. So is it unusually high? No. So we can eliminate these yeses. No, because 507 girls and 979 births is not far from what is expected given the probability of having a boy or a girl. So that's correct. This one's wrong because it says it is far from what is expected, but that's not true. Part C says which probability is relevant for trying to determine whether the technique is effective. The results from part A or the result from part B. So I'm not typically interested in getting exactly 507 girls in 979 births. So they're trying to argue that their technique produces more girls, so part B is more relevant because that looked at the probability of having more than close to the mean number of girls. We can eliminate A and D because the results are not equal and part A is not more relevant. So the answer is B. The result from part B is more relevant. Based on the results, does it appear that the gender selection technique is effective? Well, their gender technique pretty much gave us pretty close to what we'd expect, and being half the number of births were girls. There's only a 13% chance of getting more than that 507 that we saw. So is their technique effective? We would say no. So the yeses are gone. No, because the probability of having 507 or more girls is unlikely, and thus it's attributable to random chance. No, because having this number of girls is not unlikely, and thus is attributable to random chance. So that's correct. It's not unlikely. Okay, the probability 55, the probability of flu symptoms for a person not receiving any treatment is 0.027. To lower cholesterol. Assuming the drug has no effect on the likelihood of flu symptoms, estimate the probability that at least 34 people experience flu symptoms. So that's our P, 0.027. Our Q then is 0.973. Therefore, our mu is N times P, which is 1150, the number of people in the study, times 0.027, which is 31.05. Our sigma is the square root of N times P times Q. We already know NP, it's 31.05, times this Q, 0.973. So our sigma value is 5.5. So we want the probability of X being greater than 34. So we're going to correct to 33.5, just to the left of it, since 34 is to the right, and that way it'll include it. So what's the probability that X is greater than 33.5? We'll have to convert that to a z-score. So we'll have 33.5 minus 31.05, the mean, divided by the standard deviation of 5.5. And we'll get the probability of z being greater than 0.45. So if we were to draw this picture, our z-score is about 0.45, just to the right of the center. The chart's going to give us the area to the left, and if we look that up in the z-chart, that area to the left of 0.45 is 0.6736. We want the area to the right of that, so we'll take 1 minus 0.6736, which is an area of 0.3264. So what does the result from part A suggest? This is not highly unlikely, that probability, so the drug has no effect on flu symptoms. Okay, 56, assume that 36.6% of people have sleepwalked. Assume that in a random sample of 1,482 adults, that's N, 554 have sleepwalked. Assuming that the rate of 36.6% is correct, find the probability that 554 or more of the 1,480 adults have sleepwalked. So our p-value here is 0.366. Therefore, our Q value is 0.634. So our mu is N times P, which is 1482 times 0.366, which is equal to 542.41. Our sigma value is the square root of NP times Q. That NP value we just found, 542.41 times the Q of 0.634 square rooted, will give us a standard deviation of 18.54. Assuming that the rate of 36.6 is correct, what's the probability of more than 554 people sleepwalked, which is we're going to continuity correct to the probability that X is bigger than 553.5 so that we can capture the 554 because we want to include it. And this is equal to a z-score of being bigger than that 553.5 minus the 542.41, all divided by the sigma value of 18.54. This is the probability that z is bigger than 0.60. So if we draw a normal curve, 0.60 is just to the right of the center. The area to the left of that from the z table, the normal distribution table, will be 0.7257. Therefore, the area to the right, which is what we want, is 1 minus this 0.7257, which is equal to 0.274. 0.2743. So is the result of 554 more significantly high? Our significantly high criteria is if it's 5%. So we're looking for either a 95% or a 5% on one of those ends. 27% is nowhere near one of those ends. So we'd say no, it's not significantly high, because the probability of the event is greater than the cutoff value for significant events, which is 0.05. What do the results suggest about the rate of 36.6%? The result is B. Since the result of 554 adults that have sleep is not significantly high, it is not strong evidence against the assumed rate of 36.6. Okay, 57. In a survey of 1,294 people, 860 people said they voted in a recent presidential election. Voting records show that 64% of eligible voters actually did vote. Given that 64% of eligible voters actually did vote, find the probability that among 1,294 randomly selected voters, at least 860 actually did vote. So P is 0.64, and therefore Q is 0.36. We want the probability that X is bigger than 859.5, so that we can include that 860 to the right of it. That's equal to the probability of a z-score of 1.81. And that's, so we need the area to the right of 1.81. So the area for 1.81 is 0.9649 from the z chart. And so when we subtract these two, the area to the right of it is 0.0351. And now notice, now we do have a number that's less than that 0.05 cutoff that we talked about in the previous problem. So 0.03 is less than 0.05. So what does this say? It says that there's a good chance some people are being less than honest because that probability of more than 860 people saying they vote, actually voting, is less than 5%. And it makes sense. During voting season, there's a lot of pressure to vote, and people will ask, hey, did you vote? Did you vote? It can get tiresome, so it might be easier to just say, yes, I did vote, even though maybe you didn't. Okay, in this one, where I studied cell phones, we've seen before, 71 had cancer. Assuming there's no effect, there's a 0.00194 probability of someone getting cancer. We therefore expect about 79 cases of such cancer in a group of 407,000 people. Estimate the probability of 71 or fewer cases of such cancer in a group of 400,000 people. What do these results suggest about media reports that cell phones cause cancer of the brain or nervous system? So in this problem, they gave us mu, it's 79. But they didn't give us sigma, which is actually the harder number to find. Sigma, in this problem, P is given to be 0.000194, therefore Q is 1 minus that small number, so it's 0.999806. And sigma is going to be that mu value of 79 times this Q value of 0.999806. And if you calculate that, you'll get a sigma of 8.8. Now, we want the probability that X is less than, fewer than 71 people. So we're going to go with 71.5 to include that 71 because of the equal to sign. We'll convert this to a z-score by taking 71.5 minus the 79 divided by the 8.89. And we'll get a probability that z is less than negative 0.84. So we have negative 0.84 just to the left of the center. We want the area to the left of that, so we can look it up directly from the normal distribution table. That area is 0.2005. What does the results from part A suggest about the media reports? Well, there's only a 20% chance that you would get more than that number of cancers. So B, the media reports appear to be incorrect. Okay, which of the following is not a requirement for using the normal distribution as an approximation to the binomial? NP greater than 5, NQ greater than 5. We talked about that right away at the beginning of the class, so those are true. Sample simple random, size n from a population in which the proportion of successes is p, or the sample is the result of conducting n independent trials of a binomial experiment in which the probability of success is p. That's pretty much word for word exactly what it is, said even better than I could. And therefore A has to be incorrect, and it's because they're talking about dependent trials, which we very rarely want to do. Okay, last problem in this section. Which statement below indicates the area to the left of 19.5 before a continuity correction is used? So they've already added or subtracted 0.5. And so we have 19.5. They want the area to the left of that. So they either had 19 or 20 to start with. So we can identify these two numbers. 19's in the area, 20's outside of it. So at most 19. And that does it for section 6.6.